about physical equilibria, and to be specific, we are on partition coefficient, or you can call it distribution coefficient. Where yesterday we saw how we can determine the partition coefficient, Kd, of ethanoic, not ethanoic acid, ammonia, between the aqueous layer and trichloromethane. No, it is trichloromethane layer, the organic layer. And we did some good calculations and they were really good. And I hope you guys, you enjoyed the calculations. So in today's lesson, we are going to proceed with where we stopped from, where we shall determine the Kd between the ethanoic acid, the Kd of ethanoic acid and Kd of ethanoic acid between tetrachloromethane and water, where the ethanoic acid becomes like a solute that will dissolve in both the tetrachloromethane and water, and it is the same concept. Okay, same concept. So with ethanoic acid, like we said, this one is a solute in both the organic and water, the aqueous layer, whereby it will dissolve in both this and this. And if you leave the two to attain the equilibrium, then the ratio in the concentration between the two layers becomes constant, or is constant, and that ratio is the Kd. So how you can determine? It is simple. You just mix the two layers, water and the water, which is the aqueous layer, and the organic layer of known volumes. In both, the volumes must be known, because you saw that, especially that last example that we did, it is applicable here. It is going to be applied here so much. Now, after mixing the two in a separating funnel, obviously the separating funnel, the two layers, one being the organic layer and another one being the aqueous layer, then the two are immiscible with each other. So water will settle at the bottom and the tetrachloromethane layer is going to settle on top, because water is more dense than this. Then after that, you're going to add a known volume of a standard solution. In other words, you must know the concentration of the ethanoic acid that you are adding to the mixture of two. Then you cover and you shake. It is real shaking. It's not a mere shaking. It's a real shaking. Now when you shake, it's like everything will mix up. And this ethanoic acid will distribute itself equally. Not equally, but it will distribute itself in both the aqueous layer and the organic layer. And then after you've mixed, after you've shaken so well, then you leave everything to settle until when the equilibrium is attained. Now after attaining the equilibrium, you can separate, you can run off the aqueous layer from the organic layer. And after running it off, then you can titrate everything. Okay? It's like you have this. This is your separating funnel. Okay? And this is your separating funnel. So you have the aqueous layer, you have the organic layer. Okay? Let me talk about this. Then you add a known volume of ethanoic acid. Remember, the volumes are known and, by the way, equal. Okay? So when you add your ethanoic acid, then you shake, and then after shaking, you leave them to settle, to attain an equilibrium. And then after, there will be a tap here, you open the tap and you run off this aqueous layer, and then when you run off the aqueous layer, you titrate the aqueous layer. Now since it is ethanoic acid, you can use sodium hydroxide, and the sodium hydroxide should be standard. It should be of a known concentration. Okay, should be a standard solution such that you use the sodium hydroxide to standardize, to determine the amount of ethanoic acid in the aqueous layer and the amount of ethanoic acid in the organic layer. Now, after determining the amount of the of ethanoic acid in both layers, then using the equation, obviously, you know the equation, you use the mole ratio. Anyway, let's write the equation because it is important, but we know. So this will be our ethanoic acid. Okay, it will react with sodium hydroxide. This is sodium hydroxide. Let's erase a bit. Okay, so from this equation, if you know the volume of the acid that has reacted with the volume of the aqueous layer, then we can determine the concentration. We can determine the concentration of ethanoic acid in both layers. This is a minus, and then plus the water. Plus water. So from this equation, we can see that the mole ratio is 1 to 1. 1 to 1. If you know the volume of sodium hydroxide and you know the concentration of sodium hydroxide, maybe 0.1 molar, maybe n molar, you know the concentration of sodium hydroxide, then we can use this to determine the concentration of the ethanoic acid between the two layers, and from our Kd, which is concentration of ethanoic acid in water or in the aqueous layer, out of the concentration of ethanoic acid in the organic, then to give us the Kd. So from this we can determine the concentration of ethanoic acid, and then from the concentration Kd we shall get our Kd. So volume of sodium hydroxide required to reach the endpoint for the separated layers. So for the separated layers is noted, and the concentration of ethanoic acid in either layers is then determined, and then from that you can calculate the Kd. From it is going to be the concentration. We have already discussed this work, guys. So the concentration of ethanoic acid, okay, in the aqueous layer divided by the concentration of ethanoic acid in the organic layer. So from this you can find the Kd. So that's how simple, that's how cool this calculation is. Then for iodine, between tetrachloromethane and water, still the same procedure. Now the logic is, what are you going to titrate it with? That's where, if you know that, then everything becomes easy. If you know that iodine, now for ethanoic acid, we have used sodium hydroxide. You can't use sodium hydroxide again. For ammonia, we used HCl. You can't use sodium hydroxide on ammonia solution. So the issue is, which standard solution are you going to use to determine the concentration of the solute in the two immiscible solvents? If you know that, then everything really becomes okay. So even iodine, same procedure. You can see So a given mass of iodine is shaken with a given volume of a mixture of tetrachloromethane and water in a stoppered separating funnel. A separating funnel that is covered at a given until the equilibrium is attained. Here it is real shaking, by the way. It's not a mere shaking. You can do this when you go back to school. You can do this. It's real shaking so that the equilibrium is attained. And when the equilibrium is attained, you can leave the mixture to settle. And then after settling, you run you run out water and you remain with the organic layer in the separating fan. Then since you have used some known, maybe you have used the 50 centimeters cubed of water and 50 centimeters cubed of the organic layer, or you've used 25, then you can titrate the whole layer, the whole aqueous layer, the whole organic layer with a standard solution. Now since our solute in this case is iodine, then we shall titrate it with sodium thiosulfate. But now, how are you going to know the endpoint? Then you should use an indicator. And in this case, the indicator is the starch indicator. And you get the volume of thiosulfate that is required to neutralize all, not neutralizing, but to react with all iodine in both layers. Now, if you have the volumes, then can't you really determine the concentration of iodine in both layers? Yes, you can. So from that equation, you have thiosulfate, and this is thiosulfate aqueous. We studied this equation in inorganic chemistry. I think in organic chemistry, we wrote these equations. Thiosulfate plus iodine. You can use half equations. So it will give us S4 O6 O6 aqueous again plus iodide ions. And so there is a 2 here and a 2 here. So from this equation, guys, you have the mole ratio, you know the volume, then you can determine the moles of iodine in the 2 layers. And then if you know the moles of iodine, then you can determine the concentration of iodine in the 2 layers. And from the concentration of iodine, you can determine the Kd, the distribution coefficient, the partition coefficient of iodine in both the tetrachloromethane layer and the water, the aqueous layer. So basically, it's really simple. It is as simple as counting 1, 2, 3, 4 up to 5. So there is an example, but you are the one to do it. You do that. You do this. Maybe if you want me to do still, you can tell me. I'll do it. Maybe. Okay. Thanks for that. It was really a nice trial. Let's now do. Where is my pen? Okay. It's okay. So the question was really good. It is 20 centimeters cubed. Don't mind about 10. 10, it was number 10 in the topical questions. So that's why it has a 10. So 20 centimeters cubed of 0.1 molar solution of potassium iodide was shaken vigorously in a separating funnel with 20 of the organic layer tetrachloromethane. So now it is the aqueous layer of potassium iodide. It is shaken with the 20 of the organic layer. So if you are to illustrate, this is your separating funnel. Okay, so separating funnel, it's like this. So you have the 20 of the aqueous layer, this is aqueous, and you add there 20 of the organic tetrachloromethane, and then you shake. It is real shaking, not mere shaking, it's real shaking. And then after shaking, then you leave it to settle. And when everything has settled, then you run off the aqueous layer into maybe a beaker or a conical flask, and then you add the starch indicator, and then you titrate using sodium thiosulfate from a burette. And you find out that, I think it is this, you find out that the 10 centimeters cubed of the organic layer, actually here they pipeted, so here we pipeted. So we just pipeted 10 of the organic layer. It required 18 of 0.2 molar sodium thiosulfate. And it's really cool. It's really cool, man. Very easy. So let's do. So here, from that simple breakdown of the question, we want the role of potassium iodide in the experiment. It is simple. It is the potassium iodide. It has both iodine and the aqueous solution. So it is to provide the iodine which is going to distribute itself throughout. Then observation of the color changes in the organic layer, it turns reddish brown. Why? Because it dissolves some iodine from this potassium iodide. Then 10 centimeters of this organic layer required 18 of the 0.2 molar potassium, so the sodium thiosulfate solution. So it is simple from this, but I really need this pen which is permanent. I don't want to lose any work. Yeah, it is here. Good. So from this, we can get the moles of sodium thiosulfate that reacted. So we can 1000 centimeters cubed contain, I'm going to just use summaries, yes, so that we can write the whole of it on the same page. So 1000 contain 0. But I'll say everything 0.02 moles. Okay, so how about 18 centimeters cubed? Can somebody get that answer for us? 18 centimeters cubed contain 18 times 0.02 out of 1000. So what is the answer here? This is around 0.0036, something of that kind. Anyway, what's the answer? Okay, you will get it, moles. Then from the equation, and we wrote the equation up, we saw that, okay, let's write it. The equation is thiosulfate reacting with iodine, and this is aqueous. This one is also aqueous. We shall get S4, O6, and this one is also aqueous, plus iodide ions. Not so? And this is aqueous. So if you are to balance, we shall need a 2 here. There is 2 minus and 2 minus. So we shall need a 2 on iodine, iodide ions, and a 2 on this. So therefore this becomes, so from this equation we can see that 2 moles of thiosulfate, okay, react with 1 mole of iodine. It is as simple as that. So 2 moles of thiosulfate react with 1 mole of iodine. So if we divide, so how many moles do we have? How many do we get here? It is 0.
0.00.
Zero, zero.
3, 6.
How many zeros here?
0, 3.
There are 3 zeros. And then 36 moles. So 0.00036 moles of thiosulfate will react with a half of this. So this is 0.00036 times 1 out of 2. And the answer goes back to 18. So it gives us 0.00018 moles of iodine. So now this is cool, guys. You see, it is 10 of the organic layer which was pipeted. It's okay, you can mute. You can mute for a moment. So it is 10 of the organic layer which was pipeted and then titrated with sodium thiosulfate. Okay? That's good. And we have found out that the 10 contains how many moles? 0.18. 0.00018 moles. So now if 10 centimeters cubed contain 0.001 moles, 0.00018 moles. Now, I think don't take it to 1,000 because we still don't want the 1,000 here. Yes, if you take it to 1,000, it will give us the concentration. But we still want to find how many in 20. So that we get how many in 20, we determine how many remained in the aqueous layer. Not so. So therefore 20 centimeters cubed of the aqueous layer contain how many? It is 20 times 0.18 divided by 10. So it will be 20 times 0.00018 divided by 10. So it will still go back to 0.36. So that 20 contain 0.00036 moles. Okay? I hope this one is cool. I hope this one is okay. Now, if 20 were able to extract 0.0036, then how many remained in the aqueous layer? So how shall we get it? The same way we got in yesterday's one. So what shall we do? So from this 0.1 to 1,000 centimeters cubed contain 0.1 moles. Then what of 20 centimeters cubed? So we want moles in 20 before shaking it with the organic layer. So it will be 20 times 0.1. So it's 20 times 0.1 out of 1,000. So what's the answer? Jordan, what is the answer here? Let's hurry up. Okay, this is Z, this is going to be 2, so it is 0.002. 0.0002. No, it is 0.02 more. Not 002, but 0.02 more. So it is 0.002 moles. So now these are the moles of iodine in potassium iodide before shaking it with the organic layer. But now after shaking it with the organic layer, we see that the organic layer was able to extract 0.00036 moles. So what is the number of moles of iodine that remain? It will just be 0.0002 minus 0.00036 moles. So what will be the answer? So this is 36 minus, so the answer is 0.00064 moles. Now we have moles. Can't we determine the concentration? Yes, we can. We have moles here. So if 20 contain, if 20 contain 0.00036 moles, so what is the concentration then? What is 1,000? 1,000 will contain 1,000 times this out of 20. So it is 1,000 times 0.00036 out of 20. So what is the answer, guys? So the concentration, oh, it's raining here. So the concentration of iodine, I cannot hear.
0.082.
So it is 0.082.
0.82.
Molar.
0.0.
Hey, there is a zero, eh?
0.082.
Okay.
Yeah.
0.082 molar. So this is the concentration of iodine in the organic layer. Now, how about this? If 1,000 contains 0.00064, then have, oh, if 20, not 1,000. Sorry for this. So if 20 contains 0.00064, what of 1,000 contain 1,000 times this out of this. So 1,000, let me write it, times 0.00064 out of 20. So what is the answer? What's the concentration of iodine? Okay, in the aqueous layer.
0.
0. 0. 0. 0. 0.82. It is just 0.82.
0.82.
Oh, you mean it is the same? So
0.082.
0.082.
No, there.
You mean it is
Above
the
it
same?
No, above it is 0.036.
It can't be the same, man. So this one is
0.036.
0.036. Yeah, it can't be the same. You want to give me poison? 0.036. No, it can't be 36. This is 36 divided by 20. So it's 1/8. There is 1/8 something. Because if we cancel this and this, and this will be 1. So it can't be 36. You put it on the calc very well. You man. 0.018. So the KD is going to be concentration. I think here we shall let's use the aqueous layer up. Concentration of iodine in the aqueous layer. Let's use the aqueous layer up out of the concentration of iodine in the organic layer. So which is going to be 0.8 0.082 divided by 0.018. So what's the final answer?
4.5.
No, this is bigger than this.
4.55.
4.556. So this is our KD and it doesn't have units. I hope it is really okay. If it's not okay, please you can say and we repeat. You can repeat everything. There is no problem with that. Yeah, that's good, guys. So applications of this, why are we doing all of this? By the way, it is important. Number one, in solvent extraction, not attraction. This was a computer error. It is extraction. Okay? And this one is important in laboratory, as far as laboratory work is concerned. Be it molecular, be it microbiology, be it chemistry lab, industry, solvent extraction is important. Okay? Whereby you want to extract a given solute from an impure solvent, you mix it with a solvent that dissolves it more than where it is. And you extract some good amount. We can use this partition law in determining the formula of the complex, and we shall do all calculations concerning this one. Then it is important, this partition law is important in chromatography, whereby in chromatography you separate two different components having different rates of movement on the adsorbent medium. So you can also apply that law here. And since today is a weekend, we are going to stop here. Okay? Let's go and rotate. But next time we shall begin with solvent extraction. So you can do some reading. You can read through and see how the solvent extraction is really, how we can use the partition law to determine how much can be extracted, which solvent can extract which solute from which solvent, and stuff like that. So you can read ahead. So in case there are no questions, then we can call it a day. However, don't forget to subscribe by the way. It is also